Ready to go.
All right. Welcome back, everyone, to the second part of the second session on multi-party computation. Again, we'll first do all the talks. There will be 4 of them, each of them 5 minutes, and then we'll have a Q&A for all the talks at the end. The link, you should still see it in the chat where you can ask the questions on Zulip. And that's pretty much all I have to say. So the first talk will be by Yifan Song about Atlas, efficient and scalable MPC in the honest majority setting. And Yifan, if you...
Yeah, okay.
All right, perfect.
Oh. Hello, everyone. My name is Yifan Song. Today, I'm happy to introduce our recent work, Atlas, Efficient and Scalable MPC in the honest majority setting, co-authored with Vipul Goya, Hanjun Li, Ravi Ostrovsky, and Antigone Polychroniado. Multi-party computation allows several mutually distrusted parties to evaluate a function on their private inputs. In this work, we focus on the function that can be represented as an arithmetic circuit with addition and multiplication gates. We focus on the information theoretic setting with honest majority and assume a P2P channel between every pair of parties. In the following, I will use N for the number of parties and T for the number of corrupted parties. A well-known communication efficient protocol with semi-honest security was introduced by Damgard and Nelson in 2007. We refer to this protocol as the DM protocol. It only requires to communicate 6 elements per multiplication gate per party. Due to its simplicity and efficiency, the DM protocol plays a central role in the progress of efficient secure computation. Many subsequent works have used the DM protocol to achieve the malicious security with the board and guaranteed output delivery. However, any improvement to the basic protocol has been hard to come by. In this work, we improve the basic DM protocol, leading to a communication complexity of 4 elements per multiplication gate per party. We also construct a round-efficient protocol whose communication complexity is 4.5 elements, but having the number of rounds. We test our 2 constructions and compare them with the previously best-known result, GSD20. Our experiments generate a random circuit with 1 million multiplication gates. We set up our experiments in the LAN setting using the 61-bit Mersenne field. In the table, the version TWS refers to our first construction, and the version round compression refers to our second construction. The numbers in the table are reported running time in milliseconds. Our experiments show that when using the proper variant, our protocol is about 1.4 times faster than the protocol in GSD20. We also note that when the circuit depth is 20, our TWS variant works better than our round compression variant. When the circuit depth is 1000, our round compression variant performs better. In reality, we can choose the proper variant based on the circuit depth. We first introduced our construction that improved the concrete efficiency over the semi-honest DM protocol. The core of the DM protocol is its multiplication protocol. Given 2 input sharings, X and Y, the goal is to compute an output sharing of the secret X times Y. The DM multiplication protocol starts with a pair of random sharings of the same random value. We refer to these 2 sharings as double sharings. And the whole computation is led by a single party. We observe that if the leading party is honest, then corrupted parties do not learn any information, even if we do not use uniform double sharings. Therefore, uniform double sharings are only needed when the leading party is corrupted. Our first idea is to play the role of the leading party in a round-robin fashion. In this way, at least a half of multiplication gates are led by honest parties. Hopefully, we only need to prepare the uniform double sharings for multiplication gates led by crossed parties. To this end, our second idea is to use T-wise independent double share rings. This ensures that the double share rings used by crossed parties are uniformly random. We show that all parties can locally transform T pairs of uniform double share rings into N pairs with T-wise independence. In this way, we save the cost for the double share rings by a factor of 2, which leads to the communication complexity of 4 elements per multiplication gate per party. Now let's see how to reduce the round complexity without affecting the concrete efficiency. The core question is whether we can evaluate a 2-layer circuit in parallel. Indeed, the main difficulty is how to evaluate the multiplication gates in the second layer without learning the inputs. Our idea makes use of the special property of the Beaver triple and carefully combines with the DN multiplication protocol. For more details, we refer to our paper and the full video. Thank you.
Perfect. Thank you very much. And I think you may just continue with your second talk.
Okay. Yeah.
All right. We can see your slides.
Yeah. So.
Yeah. So
okay.
you can go ahead.
I just found there's a message on the chat, so just want to see whether it's a question or not. Okay, I can continue. So
yeah, we'll do the questions at the end anyway. So
yeah.
No need to.
So my second talk is about unconditional communication efficient MPC via Hausmayer theorem. This work is co-authored with Vipul Goya and Antigone Policroniado. So this slide is basically the same. So I just repeat the setting. So in this talk, we focus on the function that can be represented as an arithmetic circuit with addition and multiplication gates. We focus on the information select setting with Einstein majority and assume a P2P channel. Assume a P2P channel between every pair of parties. So in the following, we use N for the number of parties and T for the number of crossed parties. The dream in the information select setting is to achieve order of C total communication complexity or even less. Here, C is the circuit size. In the so-called optimal threshold setting, where T is equal to N minus 1 over 2, best known results require order of N times C total communication. When we move to the suboptimal case, where there is a gap K between T and N minus 1 over 2, the work by Franklin and Young showed how to evaluate K copies of the same circuit such that the amortized cost per circuit is order of C. However, the problem becomes tricky when evaluating a single circuit. No solutions either has a log C factor or a log N to the power of 1 plus epsilon factor in the communication complexity. Two recent works in Eurocrypt also try to solve this problem. However, their solutions either only achieve the desired efficiency in the offline phase or only work for a restricted class of circuits. Many attempts towards solving this problem lead to our following question. Is it possible to construct information theoretic MPC protocols for computing a single arithmetic circuit with total communication complexity order of C? In this work, we answer this question affirmatively. Our theorem shows that when K is order of N, there is an information theoretic MPC which computes a single arithmetic circuit with communication complexity order of C. An example corollary is when T is equal to 0.49 times N, the achieved communication complexity is order of C. Our work used the idea of the packed Shamir sharing. In the standard Shamir sharing, we used a random polynomial to hide a single secret. The idea of the packed Shamir sharing is to have multiple secret slots as illustrated in the picture. In general, we want to pack k-var values within a single sharing and evaluate a batch of k-gates each time. However, there are several difficulties with this approach. One of the difficulties is the need of aligning input sharings. Basic protocols for additions and multiplications only support coordinate-wise operations. To obtain the correct result, it requires the secrets within a single sharing to be in the correct order. However, during the computation, the secrets within a single sharing may not be in the order we want. It requires us to design an efficient protocol for the secret reordering. In DIK10, Damgard and others showed that the secret reordering can be done efficiently with the help of the preprocessing data. However, the limitation is that the communication overhead is proportional to the number of different permutations. In the worst case, we may need to perform a different permutation each time, which eliminates the benefits of the packed sharing. Our idea is to first prepare the preprocessing data for a limited number of different permutations, and then transform them to the preprocessing data for the permutations we want. Note that here, a limited number of different permutations means that we use many copies of the same permutation rather than reducing the total number of permutations. The core of our idea is a connection to the graph theory. House marriage theorem is a well-known theorem in the graph theory, which has many applications in mathematics and computer science. It provides a necessary and sufficient condition of the existence of a perfect matching in a bipartite graph. In a bipartite graph, a perfect matching is a set of edges such that each node has degree 1. In this work, we use a weaker version of the House marriage theorem, which states that for a bipartite graph where each node has the same degree, there is a perfect matching. Note that a perfect matching corresponds to a permutation. Now we connect our problem to the House marriage theorem. Suppose P1 to Pm are the permutations we want to perform during the computation. We first construct a bipartite graph by inserting the perfect matching corresponds to each permutation. To prepare the preprocessing data for P1 to Pm, we managed to show that it is sufficient to prepare the preprocessing data for a different set of permutations Q1 to Qm, such that the bipartite graph constructed from Q1 to Qm is the same as the bipartite graph constructed from P1 to Pm. Using the House marriage theorem, we show that we can find such Q1 to Qm with limited number of different permutations, which solves the problem. For more details and solutions to other difficulties, we refer to our paper and the full video. Thank you.
Okay. Thank you very much, Fan. All the questions, please post them in the Zoom chat, and we'll answer them at the end of the session. And we continue with the next talk by Reo Origuchi.
Okay.
Who will be talking about non-interactive secure multi-party computation for symmetric functions, revisited, more efficient constructions and extensions. Reo, please go ahead.
Thank you for your introduction. My name is Reo Origuchi. This is a joint work with Kazuma Ohara, Shota Yamada, and Koji Noida. First, we introduce a non-interactive multi-party computation. This is a variant of secure computation that allows each player to send only a single message, depending on the private inputs. In this model, players do not communicate with each other, and so they only send their messages to an output player called the evaluator. So NIMPC can realize a synchronous multi-party computation, which is especially important in applications to voting, auctions, statistical survey, and so on. We note that a standard multi-party computation assumes simultaneous interaction between players. So some player may need to wait for messages from other players. That leads to a delay in communication. Previously, it is known that unconditionally secure NIMPC for all the n input functions is possible. However, such a protocol must result in exponentially large communication complexity because of a non-lower bound. So in this work, we focus on a special class of practical functions, and we aim at reducing communication complexity of NIMPC for those specific functions. Here we summarize our results. First, we propose an efficient NIMPC protocol for symmetric functions, which are applicable to voting and auctions. Our protocol improves the best known communication complexity for symmetric functions. We also propose an efficient NIMPC protocol for linear classifiers. They include support vector machines and logistic regression. Our protocol is the first one tailored to linear classifiers, other than the general but inefficient construction for all the n-input functions. In addition, we revisit a previously known transformation technique to strengthen the privacy of NIMPC. It's an important technique for NIMPC, and actually we use it in the above efficiency improvement part of our construction. In this work, we reveal that their sub-protocol used as a building block does not satisfy the security requirements, and so their transformation technique is not secure either. However, we also propose a technique to fix their security issue without increasing their communication complexity. So in summary, their original statements still hold true, but it is necessary to replace their building block with ours. First, a symmetric function is a function such that its value does not change even if we arbitrarily permute the input variables. For this function, we propose an efficient NIMPC protocol whose communication complexity improves the first protocol. Our protocol is uncomparable to the second one, but if the number of corrupted players T is much smaller than N, our protocol is even more efficient than the second one because the exponent is smaller. Here we show very high-level idea of a construction. Following the previous work, we consider a generalized notion of symmetric functions called a abelian program. It takes as input n group elements from an abelian group G, and it computes some function f on the sum of n inputs. Our first contribution is proposing a more efficient NIMPC protocol for abelian programs than the previous one. Next, we need to restrict input domains because for this functionality, players are allowed to set their inputs as arbitrary elements in G. To restrict input domain to a subset of only valid inputs, we propose a novel application of BKR transformation. Our technique is novel because it was originally proposed to strengthen the privacy of NIMPC instead of extending functionalities of NIMPC. As a result, we can achieve a smaller overhead in communication complexity in this step compared to the previous one. Finally, this functionality includes symmetric functions, and so we can obtain an NIMPC protocol for symmetric functions. So far, we have used BKR transformation in our construction, so we revisit the original transformation technique. It transforms a weaker notion of NIMPC called private simultaneous message protocol into an NIMPC protocol for the same functionality. As a building block, their transformation is an NIMPC protocol for what they call outputting message functions. An output messaging function outputs a message M exactly when inputs satisfy a linear equation. They actually proposed an NIMPC protocol for this functionality. However, we reveal that their original protocol does not even tolerate collision of a single input player and an output player. So their transformation is not secure either. However, we propose a technique to fix their security issue by proposing a modified NMPC protocol for outputting message functions. The communication complexity of a protocol is asymptotically the same as the original one, so the original statements still hold true, but it is necessary to replace their building block with others. This is the end of my talk. Thank you for listening.
Okay, thank you very much, Rail. And we'll continue with the last talk of this session, which will be given by Eduardo Soria Vasquez, and he will be talking about efficient information theoretic multi-party computation over non-commutative rings. Eduardo, the stage is yours.
Thank you very much. So this is joint work with Daniel Escudero from Aarhus University. And I'll start if the slides want to move. Yes. Oh, wrong slides. Sorry. Sorry about that.
No worries.
Should be once. Okay. Yes. All right. So yeah, the talk, it's about the efficient information theoretic multi-party computation over non-commutative rings. And if there's one thing you have to remember about this talk is that we are the first ones to provide this result, interpreting that we work black box over the non-commutative ring. So let's start by recapping how Shamir's secret sharing works, mostly to fix some notation. So if you wanted to share some secret Y, the way you can do this using Shamir is that you sample a polynomial of degree equal to the number of corrupted parties in your protocol, such that the evaluation of this polynomial at some fixed designated point alpha 0, 0 here in the example, equals your secret. So it would look something like this. And you define the shares of every party as the evaluations of this polynomial at some designated public points, alpha I. So you give to party 1 the evaluation of the polynomial at alpha 1, and so on. And the notation I'm going to use for this is this double bracket. I will have this subscript to denote the degree of the polynomial that was used to share the secret sometimes. So the reason why this protocol is secure is because you need at least t+1 points to get any information on the secret. And the reason, so that's about privacy. And how do you get correctness is basically because Shamir secret sharing is a read-to-long code. So when parties want to reconstruct the secret, they are just going to announce their evaluations of the polynomial, and then either doing error detection or error correction, depending on the number of corruptions, parties will be able to recover the secret. Okay, so this is how it works over a finite field. And the small note before going ahead, that might sound obvious, is that you need the size of your field to be bigger than the number of parties. Otherwise, you don't have enough points for your polynomial. So if you wanted to just work with like a Boolean secret, you need to move to an extension of degree D, as we did here in the example. And this degree D is logarithmic in the number of parties. So some nice properties of Shamir's scheme is that it is linear, meaning that if you take a secret X, you can multiply it by some scalar A in the field on the left-hand side or on the right-hand side. You can sum all of these things together. What does this mean? It means that if you take this vector of evaluations of a polynomial, this constitutes a vector space over your finite field. Okay, another nice property about Shamir's scheme is that it's what's known as strongly multiplicative, meaning that if you take two vectors that are the evaluations of 2 degree T polynomials, and you multiply component-wise these vectors, you end up having what would be like a secret sharing of the product of the secrets using a degree 2T polynomial. And crucially, the reason why both of these very nice properties hold is that evaluation of a polynomial at some designated point alpha is a ring homomorphism. So it's the same thing to sum polynomials and evaluate them afterwards, or to evaluate them and then sum them, and the same thing for multiplication. This is why all of these properties work. So before moving to our result, I'll make a quick stop to talk about how do you do this over a commutative ring. This was work that was presented on TCC on 2019. And I cannot get into the details because there's not enough time. But the important thing is that as long as the points you choose for the evaluation of the polynomial for the parties, they constitute an exceptional set, which means that the difference of any two of these points is invertible. You're good to go, and everything works as it did in the field case. The problem that appears now is that if you look, for example, at the ring of integers modulo 2 to the k, this contains no exceptional set of size bigger than 2. If you take any 3 elements, 2 of them will have the same parity. So the solution now is the same that we did in the finite field, right? If you wanted to do a protocol over F2, you have to move to a Galois extension to find a bigger field. So here you do the same thing. You move to a Galois extension of the integers modulo 2 to the k. And if the size of these exceptional sets grows the same way it does in the finite field case. So if your extension is of degree d, you will have an exceptional set of degree 2 to the d. So I have this one slide about our work. So if we take the set of the evaluation points to do Shamir secret sharing over a non-commutative ring, what we first need from them is that they need to be an exceptional set, as it was in the commutative ring case. And then we have 2 options to choose from. So if this set of evaluation points is contained on the center of the ring, that means if these points alpha I commute with every other element in the ring, it's the same moral of the story as in the commutative ring case. Shamir's scheme is linear, meaning that it is a bimodule, so you can multiply with the scalars from the left-hand side or from the right-hand side, and it's still strongly multiplicative. So everything works as in the commutative ring case or as in the finite field case. But if you relax what you ask from this set of evaluation points, so that they just need to commute with each other rather than commuting with every element of the ring, you can still do Shamir secret sharing and you can still do MPC protocols. The problem, those familiar with non-commutative algebra will understand this. Those who are not, I invite you to check the full talk on the paper, is that polynomial evaluation at these points alpha I is not going to be a ring homomorphism. So it's not going to be the same thing to, for example, evaluate polynomials at some point alpha I and then multiply them or multiply them and then evaluate. So what happens with Shamir's scheme now is that you have to choose from which side you want it to be linear. So you can get either a left module or a right module, but you cannot share a secret having this bimodule structure. Furthermore, the scheme cannot be multiplicative, which is a big problem. And this makes things such as the online phase trickier. If you were here in the first talk, you saw this trick about the double sharings, which consist of, you multiply your secrets using the strongly multiplicative property, and then you put the degree down. So now you cannot do this anymore. And you have to use some kind of enhanced beaver triples to do this trick. The problem now is that you're pushing this issue to the preprocessing. And that makes things complicated, but again, we have a solution for that. And I invite you to check the full talk for these details or the paper or ask questions. So just to give a concrete example of these choices, if you wanted to do Shamir secret sharing or an MPC protocol over the ring of matrices, over the
Can I just interrupt you really quickly? Can you try to wrap up maybe?
Yeah, this is the last thing. Okay, sorry.
Okay, thank you.
Okay, so if you take this ring as an example, the center of this ring has the problem that the exceptional set is of size only 2. Whereas if you go to the more relaxed setting, you can find within it a set that is of size 2 to the n. because you can basically embed this Galois ring into the matrix. So, you know, if the takeaway from that is that you can make your ring, you'd rather to move to like an extension, which is kind of like useless space that you then need to amortize using other work or using other works. You can now use this extension degree to work with matrices that are of size at least logarithmic in the number of parties. Sorry, I went over time. Thank you.
Okay, thank you very much, Eduardo. So we'll move on to the Q&A, and I guess we'll go again in the order of the talks. So there's a question by Daniel for Ifan. Daniel, if you could unmute yourself and ask the question.
Oh, I was just going to ask for some more information about. So, what is an abelian program in the context that you're using it?
Yeah, an abelian program is a generalized class of symmetric functions. For example, if d equal to 2, that means Boolean symmetric functions are considered. Boolean symmetric function depends only on the sum of n inputs over integers. An abelian program captures that intuition and generalize it to the general abelian group.
So is it like the order of the function usage on the inputs? Is that pretty much then you can interchange the order?
Order? What do you mean by order?
The order of the abelian program being run on the input.
Yeah. The commutativity of the underlying group is necessary. Yeah.
Okay. Cool. Thank you.
Thank you.
All right. So there was just, I guess, a small confusion with all the Daniels. So there was also a question by Daniel Escudero.
Yeah, thank you. No, it's all right. So this is for Yifan regarding the first talk. Great talk, by the way. Just wondering if you, does your second protocol, I thought it was the second protocol. The second protocol implies that you can get one round communication with communication, hold on, one round multiplication with a communication that is linear in the number of parties. Is that true?
Yes.
All right. Thank you.
By the way, Ifan, so for the protocol for the T-wise protocol, is the online phase basically, does it remain unchanged? Is it the same as the DN protocol, or?
Yeah, so the online protocol is basically the same. So we just need to replace the double sharings used in the DN protocol.
Okay, thank you. And so you had this table up with the simulations. Could you? I might have missed it. Could you just say what the columns were? If you maybe can pull it up real quick.
Sorry, which one?
In your first talk, you had a table with simulation results.
Yes, maybe let me open my slide. So this one, right?
Yeah, right. So the 3, 5, 7, what was that?
Oh, yes, this is the number of parties. So we basically test the several settings.
Okay, thanks. All right. Does anybody? Oh yeah, there is a question by Anirudh. If you're still here.
I can ask it here. Okay. Yeah. So yeah, my question is for Yifan on the Hall's-Marich theorem-based one. So from what I understand, the number of secrets is traded off against the corruption threshold, right? So the more secrets you pack, the corruption threshold reduces.
Yes.
Is there some middle ground that you can reach? Meaning, can you make use of the technique to keep the corruption threshold sufficiently high, and also keep the packing also sufficiently high in terms of the exact exact cost? Like, is there like a optimal cost that you can reach where you maintain both at a sufficiently high?
So I'm not sure I understand your question, but basically, the number of secrets you can pact plus the number of corrupted parties should be no more than half of all the parties.
Okay. Okay. So maybe if you choose like maybe 1/4 for each, then you would reach like optimal like threshold and optimal communication, like gain in communication.
Yes, but I think you can actually choose it dynamically depending on the scenario. So even if like you choose 1/3 corruption threshold and you can pack 1/6 times n secrets, it's still fine, I think. So it's like you can choose by yourself, so it's not say which one is better.
Okay. Well, thank you.
Okay, there are two questions for Eduardo. Mike, can you go first?
Sure, thanks. Nice talk, Eduardo. I just had a question about beaver triples, which you mentioned very briefly. It sounded like you have to do something a little bit special for a beaver triple. Is there something you can tell us about that quickly?
Can you see the slide?
Yes.
Okay, so this is a bit like, this is from the full version of the talk. The problem with beaver triples is that you need to have this bimodular structure. If you look at the fail number 2 over there. So in order to come around this problem, rather than having a triple, you can have like a sextuplet, where you make like a you basically add this intermediate step number 2 over there in order to get all the schemes to be in the same kind of module and get your get the product that you wanted to compute. This is if you want to do like a function independent online phase, but in the paper we also show how to do like a function dependent online phase that has like the usual round complexity.
Cool, thanks.
Okay, one more question, Daniel Escudero. Oh, sorry, no. Barry, you go first. If you're still here.
Hi, yeah, I am. So in the case of non-commutative rings, as I say, you're presenting two options. Either you have it in the exceptional set in the center, or you have them that they're only commutative with themselves. Is it possible that they are not commutative with themselves, and would that deny any form of Smear-style secret sharing?
Yeah, so that's not possible, and the reason for that is that all these issues with polynomial evaluation not being a ring homomorphism. So in order to build up to error detection and error correction, you need to prove things about like the number of roots of a polynomial and things like that. So when you're bounding the number of roots of a polynomial, the usual way you would do about proving this is that you do Euclidean division successively by every root. Yeah. But now, in order to say like, oh, okay, if it's, you know, when you have two of these factors and you want to say, okay, if it's, you need, I don't want to be very long, but you need the product, the group homomorphism for the product. So otherwise you cannot keep like shaving roots one after one and reducing the degree of the polynomial. So this is why you need these elements to commute with each other.
Yeah. Okay. Very well. And then yeah, I added the question: do you have any intuition if it generalizes to replicated or even general linear secret sharing schemes?
So actually, for replicated secret sharing schemes, I haven't seen anyone claim the result in the literature, but things just work fine. The reason why, you know, we say we are like the first ones that do like efficient MPC over like a non-commutative ring is that replicated secret sharing, if the number of corrupted parties, you know, it scales not polynomially with the number of corruptions, right?
Yes, correct. Yeah. Okay, thank you.
Okay, any last minute questions? All right, we have reached the end of our slot. Thank you very much to all the speakers of the